Okay, so hi everyone who is watching from the future on YouTube. We've spent some time looking at a worksheet that I uploaded for today, which you can find on the website unless somehow the YouTube video has survived and the website hasn't. Just a couple of announcements in case you didn't see my prior email. I now have office hours, which are Mondays and Fridays. You can see the exact times also on the website. Tuesday, the last or Tuesday this week, so 2 days ago, the last problem that we were doing, I said something about the lifting correspondence, but we were running low on time and I wasn't articulating thoughts probably very clearly. So I uploaded a solution to that problem, which you can also find on the website. And hopefully that is abundantly clear. And if it's not, feel free to send me an email and yell at me. That's totally fine. And also someone let me know that the link to yesterday's notes wasn't working. So that should be fixed now. So if you try to download them and you couldn't get them, try again, they should be fine. Okay, so let's go ahead and get started with the worksheet. Is there anyone who'd like to volunteer to share a solution to any problem? Maybe question 1 is a good place to start, but if you're like, no, I really like question 4, I can start with 4. Something.
I can venture number 1, or some part of it if somebody wants to, since there's 4 parts, somebody wants to do one of the parts, I can just do the first 2 parts or something. Yeah, so the chain complex, right? It's made up of these groups. So the nth chain group is the free abelian group generated by the n simplices in this simplex K. So for C0, that would be the free abelian group generated by V0, V1, and V2. So that would be Z3, right? Similarly, C1 would be the free abelian group generated by E0, E1, and E2, so also Z3. And then C2 would be free abelian group generated by K, where the center bit, which is just C, and then everything else. And then you have a 0 on one end and a 0 on the other end. So 0, Z, Z3, Z3, 0.
And then what do the maps look like?
So the maps are going to send each chain to the boundary. So the first map from C2 to C1 is going to send the generator K to is it going to send it to the sum? I
think it's an alternating sum.
Yeah, alternating sum.
Yeah, so I'm just writing down things that you're saying, just so that way there's some record of these things. Just for the people who are, visual and like to see things written. Yeah, so alternating sum is the idea. And because these are group homomorphisms, right, I can describe the entire map by just telling you what it does to the generators. Okay. So here, I'll use a dark blue because my students have told me that that's easier to read. K is sent to, let's see, should I write this in terms of e's? Yeah, I should write this in terms of e's. E0 minus E1 plus E2. And there's actually a nice formula for these. If you label, if instead of looking at E1, E0, E2, you look at this as V2, V1, V2, V0, and V1, V0, right, as these three edges, right? Then the boundary, and this is any boundary, right, of any word, VI0, VI1, all the way up to like VIM, right? This is the alternating sum where J starts at 0 and ends at IM of -1 to the J. And then you take the word where you remove the jth entry. Or I guess instead of, yeah, I sub J. Or maybe just J. Yeah, you just remove the jth entry. No, I sub J. So if I apply this boundary map to K, right, that's the boundary map applied to V0, V1, V2, because that's what K looks like if I write it as an element in terms of the vertices, right? Then following this formula, I get -1 to the 0, where I remove V0. So I'll just write that explicitly because it's the first time that I've written it. Then I'm going to add -1 to the 1. I remove the V1 term, not to hijack Anthony's wonderful explanation. -1 squared, V0, V1, V2 gets removed. And when I do the simplifying, I get V1, V2 minus V0, V2 plus V0, V1. And when you look at these are exactly E0 minus E1 plus E2. So, okay, cool. So who can tell me what this, so this boundary map and this boundary map are the only interesting ones, right? All of the other boundary maps are just the constant zero maps, right? Right, this one, it's just 0 goes into a group, and the only way to do that, if the group homomorphism is sending the identity to the identity. So this is the 0 map over here, right? And this is also the 0 map because, right, I'm just collapsing my entire space to 0. So who can tell me something about what happens to this second map, right? This is the other interesting one.
Well, V2, V1 just sent to V2 minus V1, and kind of like the same thing for all the other with edges as well.
Yeah, exactly.
In the way you've written them, it's the first vertice minus the second one.
V1 minus V0. Yeah, exactly. This is good because when you want to commute the homology, which is step 4, right, you have to commute, right, you have to calculate, right, the kernel mod the image, right? So you want to know what the actual maps are because you want to be able to compute the actual kernels and the actual images, right? Cool. So even though I just said that this is a boundary thing and I gave like a purely algebraic way to compute the boundary, which is quite nice, there's also, right, if I draw a picture, okay, right, and I'll just V0, V1, V2. If you use the right-hand rule, right, where you curl your fingers and your thumb is pointing towards you from the screen, right, then the orientation of the vertices and the orientation of the sums that we just computed down here, right, match exactly the right-hand rule, right? So the positive edges E0 and E1. So this is E0 and this is E1, this is E2. But if you use the right-hand rule, just following the direction V0, V1, V2, right, you will find that E2 and E0, right, follow that right-hand rule, right? So the right-hand rule gives me an orientation of K like this, right? And the orientation on E2 goes from the lower index to the higher index. And this one goes from the lower index to the higher index. But here, the lower index to the higher index is in the opposite direction of the right-hand rule. So it gets a negative sign, whereas the other two get a positive sign, right? And so, right, this alternating sum, these positives and these negatives, right, are actually reflecting like this orientation fact, right? And so I would shortcut, right? Instead of using the formula, I would just, throw the signs on them based on their orientation of the simplex. Okay, cool. Thanks, Anthony. Okay. Would you like to continue with part B, or would someone else like to jump in for part B?
I can try part B.
Sure. Would you like to share your screen, or should I continue to note on mine?
I'm writing on a different thing, so if you
Okay.
could write on yours, that'd be great. Sorry.
More than happy.
This one I was actually a little bit confused about. When we consider the union of E0, E1, E2, does that automatically include the vertices into our subcomplex?
Yes, because if I do not include the vertices in the subcomplex, it is not a simplicial subcomplex.
Okay.
Right. Yeah, simplicial complexes always have to include the faces of whatever object you're looking at.
Okay, great, awesome. So then that would give us that the C1 of L is Z3. C0 of L is Z3, and then the rest are 0.
Yeah, so C2 of L was the only one that changed. Maybe you can say something about why it changed.
Well, like the inside, it's like we don't have a 2 simplex anymore, because like the inside is gone.
Yeah, these are generated, or at least C1 and C0 are just generated by the same 3 1 and 0 simplices respectively, right? But C2 no longer has a 2 simplex to generate, right? Because we removed it.
Yes.
Yes.
Yeah.
Okay, cool. And these maps are right,
they should be the same.
Yeah.
Right?
Yeah, there's only one interesting map and it's the same.
Yeah.
Okay, cool. Thank you. Nice and fast. All right, for 1C, right, we compute the relative chain complex. And since this is just, I mean, these have all just been computations, but maybe this one is simple enough that I should just write it, right? So, right, I take, right, so I'm just taking C3K and I'm modding out by C3L, and then I'm getting C2K and I'm modding this by C2L, right? And this continues. So just filling in from above, I have 0 mod 0. Then I have Z mod 0. Then I have Z3 mod Z3. Z3 mod Z3. And then I have 0 mod 0 again down here. So this is C3 of the pair K comma L. This is C2 of the pair K comma L. C1 of the pair K comma L. And C0 of the pair K comma L. Simplifying these down and just, right, simplifying these down in the world of abelian groups, because in like the algebra sequence here, right, we normally write these as like 1, right, for the trivial group, right, instead of 0, right? So it might be like, wait, why are we dividing by, y'all are smarter than that than to be tripped off by dividing by 0, right? So I'm taking Z, I'm modding out by nothing, so I get Z. I take Z cubed, I mod out by everything, so I get 0. Mod out by everything, I get 0. And that's also 0. All of these maps are boring. Right? Every single map here, right? All maps are the 0 map. So then what's going to drive us home here? Right, if I'm going to commute the relative homology groups.
We just have to take the kernel of a map over the image of the previous map. And so the only interesting case is in the second degree.
Yeah, so if this is so let's see, this is D2, this is D1, D0, D3, right? And these boundary maps, the subscript on them is always referring to the domain, right? The dimension of the domain, right? So D0 is the boundary map on the 0-dimensional simplices, right? D2 is the boundary map on the 2-dimensional simplices, right? Right. But since all maps here are the 0 map, right? What happens here is that the image, right? This is just the kernel of Dn mod 0, right? For everything. Right? And so what happens here is that you just get that the nth relative homology of KL is just exactly the nth chain relative, the relative chain, right, of KL for all n. And yeah, you're right, there's only one interesting case, which is D2, right? But since I'm not modding out by anything, I'll just get that. We're good, right? Another way to think about this is that this condition tells you that the sequence was already exact, right? And what this is doing, right, the kernel, taking the kernel and modding out by the image, this is exactifying the sequence. Right? And when you exactify the sequence, that's what gives you, right, the homology. But this is telling us that this sequence is already exact, right? So therefore, it's already the homology. Also, exactifying is just a fun word to say. So, okay. Questions, comments, concerns, complaints? All right. In that case, are there any volunteers for the next question?
If anybody got the Mayor Via Torres work in number 2 or 3, that'd be awesome. But I got a little stuck.
I could try 2. I don't know if this is a good description, but there are inclusion maps from A intersect B into A and A intersect B into B. And they both take cycles to cycles and boundaries to boundaries, so they induce maps on homology. So that's map number 1.
Okay, so almost. That's not what I'm looking for. Okay. So the Meyer-Vitor sequence actually has a specific map 1, but maybe it'll be more clear if we talk about what map 2 is. So do you have any guesses for what map 2 is supposed to be?
It's like the difference of like the map from like A to X and B to X.
Yeah, so for map 2, I can take UW and map it to U minus W. Okay, that's totally fine. So in order for this sequence to be exact, what does that have to make map 1? Okay, I want the kernel of map 2 to be the image of
the
map
image, 1. Yeah.
Yeah. So if I take an element V, what does V have to map to?
Like V minus V.
Just V comma V.
Oh,
because
V,
you're
yeah,
subtracting
yeah,
right?
because you subtract
Yeah,
the map.
because what you need is that the image of this thing, right? You want that this thing goes to 0.
Yeah,
Okay,
yeah.
that's exactly what you have. These are the same. The other way, and this is the way that I prefer, so like this is how I write it, is that I put the negative in the first map, and then the second map is just summing. Is U plus W. But these are equivalent. It actually doesn't matter which one of these maps that you take. You can show that these 2 maps are conjugate to each other in both cases. And so it doesn't actually change what's going on in the homology. So either one of these 2. Sometimes OneNote just doesn't let me change colors by clicking the preview. So either.
And what's the map out of Hn of X? Is that just like
that's the boundary map.
Restricted to like A intersect B? Or
I believe it comes from the snake lemma.
yeah.
Yeah, so I don't know how
Yeah.
to picture that.
Yeah. To be honest, I don't know if I've ever had to know what the boundary map actually is, other than it's a boundary map. It's the map that you need in order to make the sequence exact. And that's all that I think of it as.
Yeah, fair enough.
And although one can say many things about Schultz's teaching style, the notes that he has written, that he has on his directory for the class, is like a really well-written textbook for algebraic topology. So I'm sure that the answer is in there somewhere. Yeah, so these are the 2 maps. That's all that I wanted you to describe, was that these maps do these specific things. Because what happens when you're, like, for example, in question 3, right, when you were asked, hey, what are these homology groups, and you're using the Meyer-Vitor sequence, sometimes you can just be like, hey, there's a 0, an unknown group, a group, and a 0. Yay, that's an isomorphism, so I know what that is. But sometimes you just have like a sequence of like 3 or 4 groups in a row, and you want to use the actual definitions of these maps in order to figure out what the homologies are, right? Or what the homology groups are. Okay. Okay, so anyone for 3? I don't blame you all if nobody wants to volunteer for 3. That's the only one in my notes that took more than a page for me right now.
Yeah, I'm pretty sure how to set this up, but when I actually computed it, I got something that I know isn't right. So
I can try.
Well, you've tried a couple of these.
Yeah.
So
if someone-
not that I want to discourage you from volunteering, but maybe it could be nice to hear from some other people. Something tells me that I'll have a couple of people volunteering for 4. That's because for question 4, I just pulled that from last year's final exam that Schultz gave. So there's a couple of people who took the sequence this year that are like, I did this question, I know it. Okay, maybe we'll get a volunteer for 3, but and maybe because we only have 25 minutes or 15 minutes, depending on how you count, maybe I should just blitz through 3.
yeah, I mean,
Okay.
I can talk about how I set this up if that's
Yeah,
okay.
blitz through, Jacob.
Okay, sure. Okay, so the way to use the Meyer-Vitor sequence to compute this homology, so you have S2, which I can draw as a sphere. Maybe the more amazing fact is that I can draw it. And I'm going to set up 2. So Meyer-Vitor, as explained in question 2, right? I need 2 sets A and B, right? And for A and B, I'm going to choose, right, these disks around the sphere. So here's A and here's B. And their intersection, which the Meyer-Vitor sequence also cares about. All right, if I can draw this nicely, I will endeavor. Right, is like this lampshade, right? So some people like this to be explicit, and so if I write S2 as the set of x comma y comma z in R3, right, such that, right, the length is 1, then we can write A as, say, the xyz in the sphere such that z is less than or equal to like 1/2. Right? So I'm just taking my sphere and I'm like dividing my sphere into like unequal quarters, right? Where this is like the z equals 0, and this is like z equals 1/2. And I'm just cutting my sphere and taking everything below that line. And then B is defined similarly. Okay. Z less than or equal to 1/2. And then A intersect B is the intersection, right? And so this is kind of nice because in homology, right, A intersect B is the same as S1, right? There's a deformation reach. In fact, I think that there's a strong deformation retract, right? This is an annulus, right? Topologically, A intersect B is an annulus, and an annulus has the same homology as a circle. Right? And I gave you all the homology groups of circles, which is nice, but also A and B are each in the same homology class as R2, right? And we should know what the homology groups of R2 are, but in case you don't know what the homology groups of R2 are, right? They are 0 for almost all of them, and Z for the 0th homology. Okay, and because I couldn't remember what the homology group of R2 was, I actually did it as an exercise last night. And since I already calculated what the chain complex for the 2 simplex was, right? We did that for question 1A, right? I just did kernel mod image on that just as an exercise to remind myself that kernel mod image is a thing. Although at this point, I feel like that I would be a poor instructor if I did not give the following fact, which is quite nice, right? For any x, H0x is the free abelian group which is generated by the path components. Of x, right? So R2 has one path component, so its 0th homology is just the free abelian group with one generator, so it's Z. Right? But if you have a space that has multiple path components, then its 0th homology will just be Z raised to the number of path components. So this is nice. So we'll do this Meyer-Vitor sequence, but we don't have to calculate the 0th homology. I know what the 0th homology for S2 is. It's going to be Z because it has one path component. Okay. Okay, so, and let me also, I'm just going to move this up to the side so that I can write this next to this, right? Let me just copy down what the S1 homology is, right? It's Z for Q less than or equal to 1, and it's 0 for Q, not G, Q greater than or equal to 2. Okay, so all the interesting homologies happen for Q around 2. So first I'm gonna let Q be greater than or equal to 3. And I'm gonna look at the Meyer-Vitor sequence for Q greater than or equal to 3, so that way we can figure out what like all the large homologies are. Spoiler alert, they're gonna be 0. Right? So if I copy down the Meyer-Vitor sequence here, right, I have HQ of A intersect B. This goes to HQ of A direct sum HQB, which goes to HQX, and in this by boundary map goes to HQ minus 1 of A intersect B again. Right. So the smallest that Q minus 1 can be is 2. Okay, so plugging these things in, right, what do I get? Well, A intersect B, I already said that that's going to just be the circle, right? A and B individually are just R2. This direct sum of R2 and R2. X is the circle, or the sphere, sorry, that's what we're interested in looking at. And then this is just HQ minus 1 of S1 again. This should be fine. Okay. So plugging in these homologies that I already know, right? This is a high circle homology, so this is 0. This is high homology in R2, R2, so that's the direct sum of 0 and 0. Then I have HQ of S2. And then this is 2 are bigger, right? Since Q is bigger than or equal to 3, Q minus 1 is bigger than or equal to 2, right? And then just reading this off, hey, for Q greater than or equal to 2, right, my circle homology is 0. So this is just 0 again, right? So this is an exact sequence. Okay? So I have 0, HQ, S2, 0 in an exact sequence. And that exactly means that HQ of S2 is also 0. Right? The image is equal to the kernel. Right? But the only way for the image to be equal to the kernel here is, okay, the image being 0, right, says that this map is injective. The second map is injective, right? But the only way that I can inject a map into the trivial group is if the group is trivial, right? So the group is trivial. Okay, so now we just have to look at the small homology, right? And like I said, we also, this is for Q greater than or equal to 3, but I also know that H of 0 of S2 is equal to Z, right? By that fact that I said, right? So I only have to look at the case for Q equals 2 and Q equals 1. Those are the only ones to parse here. So let's just write out the sequence for these. So I'm going to start out with boundary map. H2 of S1, this goes into H2 of R2, direct sum H2 of R2, and this goes into H2 of S2, which is what I want to figure out. I'm going to write the boundary map over here, H1 of S1 into H1 of R2, direct sum H1 of R2 into H1 of S2, boundary map H0 S1 into H0 R2, direct sum H0 R2, H0 S2, 0. Okay, so, and actually let me just give me a little more space between these lines. I'll just try to write like in between. It's clear. So again, we're gonna fill in with the stuff that we know, right? So we know that this is 0, this is Z, and this is Z, right? Just filling out the information from the homology groups of the circle, right? I know that this is 0, direct sum 0, and that this is 0, direct sum 0, but that this is Z, direct sum Z. And then this H2 is unknown, H1 is unknown, but as we just stated, that's Z, right, from the fact. Okay, so looking at this one, a different color, should let me, right? So if I look at this one and I just break apart this one real quick, right? What I have is 0 goes to H2 of S2, which goes to Z, which goes to 0 in an exact sequence. And this is exactly the condition, pun intended, right? This means that the middle map is an isomorphism. Right? When you have 0, group 0 in an exact sequence, right? This right side is telling me that the middle map is injective. Right? The far left side is telling me that the middle map is surjective. Right? If you just think through the image is equal to the next kernel, right? Here the image is only 0, right? So right, the next kernel, yeah, right? It's okay. You're welcome. Bye. Okay. So this, going back up here, tells me that this group is just Z, because it's isomorphic to Z. That's what we proved out. Looking at colors. orange, if I look at this group, right, I have something slightly more complicated, but it's okay. I have 0 goes to H1 of S2, which goes via boundary map to Z, which goes to Z direct sum Z, like this. And I might as well just finish this off, right, for funsies. And remember, and this is why I had you do question 2, that this is the map which takes V to V comma V. I think this is the map which takes U W to U minus W. I need to use Ryan's version. Okay. So trying to figure out what this is, right? So I have that the image of this map is 0. Okay, so that means that the kernel of this map is also 0, i.e. this boundary map is injective. Right? Okay. So I have that H1 of S2 injects into Z, right? And that's nice. I also know, right, that the image of this map, right, the image of this map is Z, right? This is singularly generated by, right, the image of this map is exactly equal to V comma V, right? It's a cyclic subgroup generated by V comma V. Or 1 comma 1, if you'd like to do that, right? You just map the generators through a group homomorphism and you get generators for the image, right? So that means, right, that the kernel, oh no, sorry, I don't want the image. I want the kernel of this map. However, the kernel of this map is, so the kernel of this map is 0, right? Because this is an injective map by construction. This kernel of this map means that the image of this map is 0, right? So the only way that I can inject something that has an image of 0 is if this is equal to 0, right? So I have, right? So H1 of S2, just to summarize into Z, is an injective map with trivial image. Well, the only way to inject into a trivial image is if your domain was the trivial group, right? So that means that this group is actually 0. Right? And the only way that, and so for all of the groups except for this one, well, that is a much too dark red for a highlighter. That's still okay. That's fine. Right. So for all of the groups except for this one, we were able to figure out what they were just by using exactness properties. Hey, this is injective and this is surjective, so therefore this is an isomorphism, or right, this is just 0 because it has 2 zeros on either side or something like this. This group was the only group that we needed where we actually needed to know what these functions down here did, right? And that happens sometimes in the Meyer-Vitor sequence, right? Anyway, to summarize what we have just done, we have that HQ of S2 is Z for Q equal to 0 R2, and it's 0 for all other Q. In fact, now that you know what the S2 homology is, right, you can use the Meyer-Vitor sequence to compute the S3 homology, right, using the same idea, right? You just break it up into 2 disks and their intersection will be S2, right? And then you use the same thing. So in general, HQ of Sn is Z if Q is equal to 0 or N, and it's 0 for all other Q. And it actually gets easier as you go up, because the N case gets farther and farther away from where this stuff happens, right? And so you're just dealing with this same case over and over and over again. And then the other case gets far away and becomes very easy to do. So this is actually like the hardest one, quote unquote. All right, questions, comments, or concerns? Okay. If there are no questions, comments, or concerns, I'm going to assume that this means that my explanation was abundantly clear, but maybe it wasn't. You're just too shy to say that I'm wrong, which you shouldn't be. I'm just some schmuck who they somehow decided was qualified enough to do this. Okay, for question 4, all that this requires is that you know what the long exact sequence of relative homology is. All right, and the long exact sequence of relative homology is, so I have a boundary map, which I'm going to ignore for a second. I have that Hn of A, this is induced by inclusion into Hn of X, which is induced by inclusion into the pair Hn of X comma A, which then boundary maps into Hn minus 1 of A. And I'm going to give myself slightly more space so that way I don't leave my long exact sequence hanging. There we go. Dun, dun, dun. The way that I like to think of these as induced by inclusion is actually to write these when I'm thinking about them, or I think about these slightly differently, like this. So these are all the same homology groups. Right. Right. Because what's the relative homology, right? This is just Hn of A mod Hn of the empty set. And when you mod out by the homology of the empty set, that makes it really clear that this homology and this homology is the same. Right? Because I'm modding out by 0 every time, right? The homology of the empty set is 0 for all n. Right? But then it makes kind of sense that, hey, A comma the empty set, this includes into X comma the empty set, because A is a subset of X and the empty set is a subset of the empty set. This is just inclusion in each coordinate of the pair, right? And this includes into X comma A, because X includes into itself and the empty set includes into A, right? So both of these maps of long exact sequence are induced by inclusion. And that's a really useful thing to keep in mind when you're trying to remember the order that this long exact sequence goes in, right? The boundary maps are just the maps that you need on the end to make it a long exact sequence. And the maps in the middle are just the ones induced by inclusion. And that helps you remember what the order is. Anyway, so you look at this long exact sequence. And if I shift this long exact sequence over 1, so that way I have, let's see, Hn plus 1 of X comma A maps via boundary map into Hn of A, which maps into Hn of X, which maps via boundary map in, not boundary map, which maps into Hn of X comma A, which then boundary maps into whatever. The crux of the problem is that if this is an iso, then what I said at the end of the last step is that having an isomorphism in an exact sequence means that the ends are 0. And conversely, if the ends are 0, then you can conclude that the middle map is an isomorphism. Right? And that's all Schultz wrote for question 4, right? Right? Is that in an exact sequence, This is if and only if G to H is an iso. So if you have that these, and that's all that you use. You just look at the isomorphisms and you say, oh, that means that these are 0. And then you say if these are 0, then that means that the middle maps are isomorphisms. And that's it for me. Yeah. I'm sorry to Jennifer, who had to leave early. And then I finished 2 minutes after she left. So she's gonna like go to the YouTube video and be like, I only missed that much. You know? Okay. Any questions on number 4?
Did you use the triviality of the homology groups with the like that part right there? The if and only if part, all the relative homology groups are trivial?
Yeah, so once you have this fact, which is just a straight algebra fact,
Mhm.
right? If so, I'll walk through one implication slowly, but it really is just applying that if and only if, right? So assume, say, that this map is an isomorphism.
Mhm.
Well, using this fact, this function is an isomorphism if and only if the exact sequence has 0 going into the first group and 0 leaving the second group.
Mhm.
Right? So the fact that this middle group is an isomorphism, that implies that this group is 0 and that this group is 0.
Mhm.
Right?
Right.
Vice versa, if you assume that the groups are 0, then you go this way and if and only if, and you get that the middle group is an isomorphism. Yeah. Yeah, and this proving that this exact sequence gives you that the middle is an isomorphism is just a straightforward application of what it means to be an exact sequence.
Right.
Yeah. So yeah, and so this is a problem which maybe could have been like interesting to try to figure out how to do, except Schultz handily provides you with that hint, which tells you to just look at the only long exact sequence that you know, which has relative homology in it, and then it just stares at you. And this is how Schultz writes problems. Right? Okay. Maybe I should have stopped the recording before I said that out loud,
Mhm.
but I didn't. So I'm going to stop the recording now. Goodbye, people on YouTube.